In learning objective B, we're going to understand the law of large numbers and the law of averages. So let's talk about the law of large numbers first. Suppose that in an experiment, the event E has a probability of P. Again, let's say we're rolling a die and we want the 1 to show up. So the probability is 1/6. Then, if the experiment is repeated again and again, the relative frequency of the event will approach P. Remember, relative frequency, you guys, is percent. So they're saying the more and more you do an experiment, the percent of outcomes on that experiment should actually become what we expect it to be in theory. So let's look at this example. There's this experiment, it's Courich's experiment, and he actually tossed a coin, let's jot this down, 10,000 times, and in that he got heads 5,067 times. Okay, so they want us to figure out what is the expected count of the number of heads. So the expected count, remember, is n times p. So we did this 10,000 times. The probability of getting heads on a coin is 1/2. So we would expect it to happen 5,000 times. Okay. Part B, find the difference between the observed and the expected. Well, the observation is right here. So we observed it happened, 5,067. We expected it to be 5,000. So the difference is he has 67 more observations of heads than we would have expected. Part C, what was the relative frequency of getting heads? Well, his relative frequency, the theory says 1/6, but what did he get? He got this much out of 1,000 or 10,000. And if you do that, you'll get 0.5067. Now keep in mind, in theory, the probability is 1/2 or 0.5. So part D, what is the difference between the relative frequency and the probability? So our relative frequency was this. The probability as a decimal is this. The difference is 0.0067. So that is about a 0.67% difference. Now, as a mathematician, you would question that and decide if you think this coin is fair or if maybe it's weighted towards the head side. This seems reasonable that the coin might be fair. It's getting pretty close to the theoretical answer. Let's check out one more. Consider the following experiment. 2 6-sided die are thrown 1,000 times, and the sum of the numbers are recorded. A sum of 7 happens 175 times. Assume the dice are fair. The expected counts, if we do it 1,000 times, the probability of getting a sum of 7 is going to be a 6 and 1, a 1 and 6, 5 and 2, 2 and 5, 3 and 4, 4 and 3. So we have 6 outcomes. So the probability is 6 out of 36 because it's 2 dice. This will actually simplify to being 166 and 2/3 of a time. So we would expect that many outcomes in theory, but we had it 175 times. The difference here is 175 minus the 166 and 2/3. So the difference here is going to be 8 and 1/3. Now the relative frequency, it happened 175 times out of the 1,000, so that's 0.175. Difference between relative frequency and probability. Again, relative frequency was this. Probability, if we do 6 over 36, is going to be 0.166. The difference here is going to be this value. Now, we've been talking about the law of large numbers, so let's just recap on that. Here's an experiment that's happened many, many times, and the count of experiments goes up. The theoretical probability they expect is 50% or 0.5. Now, they did an experiment, 1, 2, 3 times. They computed the relative frequency, and they're way off. They're way high from the theoretical probability here on the green line. Now, the more times they do the experiment, they see the relative frequency starts to get closer to the theoretical probability, and it's still bouncing around the green line, but it's getting really close to it. So this is just a visual representation that says the more times you do an experiment, you should expect the relative frequency, which is all the little red dots here, to get close to the theoretical probability, which is the green line. Now be careful, the law of averages. There's a big fallacy that people make. Again, we're going to have here all of our experiments that we're seeing. So they did the experiment 10 times, 20 times, 30 times. And what they did on the averages is they just computed at each level of the experiment. So right here at 3 trials, they said take the number of heads minus the total number of tails. So when they did 3 tries of it, they had 3 heads and no tails, so 3 minus 0 is 3. They recorded the difference was 3. When they hit the 15th trial, they took the total cumulative heads minus total cumulative tails, and it looks like we were just 1 lower. Well, what this says is you're going to see it starts bouncing around the green line, but it doesn't mean it has to stay there. It could be that we end up getting a lot more tails, 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 tails. And here's the fallacy again, the law of averages. When you're down here and you're so far away from the theoretical probability, the problem people make is they're at this dot, and when they're coming up to this next try, they're like, we've had tails so many times that we have got to get heads this time. They say you have to. There's a higher chance of getting heads, and that's wrong. Every single time you flip that coin, it is a 50-50 chance. It will never, ever be different. So if you hear someone say, okay, I've had all these tails, 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 I've got to get heads this next time in this spot, that's wrong. They are defying the law of averages, and they think it should happen next. It's always a 50-50 chance.